All right, howdy folks. Happy Monday. Today is going to be day 2 of solving trig equations by factoring. So to recap, on Friday, we did some greatest common factor business. Today we're going to be getting more into what we traditionally think of factoring, that is quadratic factoring. And you might be able to tell that from your warm-up, all right? So I will also say, if you stuck around for the bonus problems at the end of Friday, you're going to have a little bit of a leg up here. But there's still a lot to sort of go through. So make sure that if you are going to go sort of off script without the video, just check back in and make sure that you're getting these answers at the end. All right. But otherwise, this time is for you to do your warm up. Hopefully it's a quick one. So go ahead and pause the video now and factor both of these expressions. All right. And we're back with some answers. So go ahead and check your work. Hopefully you got what I got. All right, but your ability to factor just normal quadratics with just plain old x is going to be kind of fundamental for what we do with trig equations moving forward. All right, so let's go ahead and try out example 1. So I'm going to scroll on down here. We are solving the equation tangent squared of x minus 2 times tangent of x minus 3 is equal to 0, and we're doing that over the interval. Over the interval 0 to 2 pi. All right, now I'm going to tell you something here that is not necessarily like mandatory or always necessary, but if it helps you, feel free to do it. Let's remember back in the fall semester that we did something called U substitution. So in this particular instance, I see that I've got a tangent of x hanging out all over the place, and I just want to swap it out. So I'm going to go for a U equals tangent of x, right? What that allows me to do is rewrite this quadratic as u squared minus 2u minus 3 is equal to 0, right? So the first few times that you're doing this, you can see how that's probably less intimidating than doing all the stuff with tangent squared and tangent and all that jazz, right? Once you make that substitution, hopefully you recognize it as just a straightforward quadratic that we will factor and then solve. Right. So also, if you're paying attention, this is the same quadratic expression that we used above in the second part of our warm-up. So I will just go ahead and copy those factors down. And now that we've got an equation in factored form that is equal to 0, we can use the zero product property and say that each of our factors is equal to 0. So I've got u plus 1 is equal to 0, and u minus 3 is equal to 0. And now I'm able to solve each of those individually. So u is equal to -1, and u is equal to +3. All right, at this point, we've gotten u by itself, so let's go ahead and make that substitution back. So we wanted to solve for x originally, so we have to take u back out of the equation. So tangent of x is equal to -1. Then over here, tangent of x is equal to 3. All right. The other thing I'm going to remind you is that you should be on the lookout for whenever you can use your unit circle values. Not everything needs to be a calculator problem. So when we see tangent of x is equal to -1, that should set off some alarm bells in our head, because we know that -1 is a nice tangent value on the unit circle, right? That is occurring at the angles of 3 pi over 4 and 7 pi over 4. All right. When we have tangent of x equal to 3, though, that is not a nice unit circle value, so we will have to use our calculator for that. So we'll set up the inverse trig. So x is equal to the inverse tangent of 3. And in this particular case, I'll plug that into my calculator, and I'm getting 1.249. All right. And so then I can go ahead and set up my axes again. Tangent is a positive ratio, +3. So my angle will hang out over here, which means that the other tangent value will be in quadrant 3. So 1.249. And then our other angle down here, if both of these reference angles are 1.249, this will be pi plus 1.249, which is approximately equal to 4.391. All right. And then we just need to make sure that we're checking our restrictions here. So for our restrictions, because tangent is discontinuous, because it is undefined in certain spots, we need to check our restrictions. To do that, we're going to recall that tangent of x is equal to sine of x over cosine of x. So as a result, cosine of x cannot equal 0. And the values where that would happen are pi over 2 and 3 pi over 2. So x cannot be equal to either of those measures. Right, that works out for us because we didn't get that with our solution, so we don't have to eliminate any of our solutions. So we'll just copy down our restrictions there, and then we have 4 total solutions for x. So x is equal to 3 pi over 4, 7 pi over 4, 1.249, and 4.391. All right, so now let's go ahead and move on to example 2. All right. And then also remember, you don't need to be doing the restrictions at the end necessarily. You can really do that at any point in the process, especially at the beginning, because really what you're checking are the restrictions at the very, very beginning, whatever was printed on the paper. So we can look at our equation here and see that we're just using cosine. Cosine has a domain of all real numbers, so there are going to be no restrictions on our equation. So we can just write none for restrictions. And then we don't have to worry about any restrictions at all. All right. I'm not going to do a substitution here. One, because like I said, the substitution is not mandatory. You don't need to do it. But also because I can look up above at the warm-up and see, oh, right, this is another quadratic that we just factored in the warm-up. So recalling, and I'll even scroll back up just to point it out, recalling that our 2, -5, and 2 in that quadratic format will factor down this way. I can go ahead and just sort of copy from above. So as we factor, that means that 2 cosine of theta minus 1, right? We're not using x, we're using cosine of theta. And then cosine of theta minus 2 is equal to 0. Right, I really do hope that you're picking up on this, that it's very, essentially, it's the same as quadratic factoring. It's just x is not our variable. We're using cosine of theta in place of x. All right, but we've got it factored now, so we can use our zero product property. So 2 cosine of theta minus 1 is equal to 0, and cosine of theta minus 2 is equal to 0. Each of our factors individually equal to 0. And then I can add 1 and divide by 2, quick maths. So cosine of theta is equal to 1/2. Then I can add 2 over here. So cosine of theta is equal to 2. Right, again, you don't necessarily need to be picking up your calculator for every single answer. In fact, that actually may hurt you, because for something like cosine of theta is equal to 1/2, right, this equation here, if you pick up the calculator, it's going to give you a decimal answer, and you'll write down a decimal answer, and that's ultimately not the best answer. What we're looking for here is an exact answer, because it's one of our unit circle values, right? So make sure that you're on the lookout for that. Basically, at which angles is cosine of theta equal to +1/2? That would be happening at pi over 3 and 5 pi over 3. Right? If you are in need of the visual here, we've got our axes, +1/2 about there, so our cosine values are there and there. Right? Pi over 3 and 5 pi over 3. Right, and now we can look at our second equation. Where is cosine of theta equal to 2? Don't think too hard about where that is on the unit circle, because remember that cosine has a range of -1 to 1, right? So we know that in the unit circle. We also know that by our cosine graph. So that would mean that theta, has no solution for this second part of the equation, right? There is no theta that will give us a cosine value of 2. All right, here's the other part. Make sure that you're on the lookout for what the instructions are for any given problem. If it was just solutions from 0 to 2 pi, then we can just write these two numbers and call it a day. but this is for all real solutions of theta, all right? So that just means that we need to adjust with our plus 2 pi k at the very end. So I'll write up both my solutions here. So pi over 3 and 5 pi over 3. And then both of those will get a plus 2 pi k for each coterminal angle after that, right? And then don't forget this bit where k is an element of fancy z, all of the integers. Also, this is my reminder that you're going to be getting scores on standard 4. There are very specific things we're looking for in the formatting of this. The characters are also very important, like this, don't mess up your, is an element of symbol, don't mess up your fancy z, things of that nature, right? 2 pi k, when it's appropriate, you know, that part is important. So just be on the lookout and make sure that you're getting that formatting and that notation down. All right, let's just take a look at the problem one last time. If you need a moment to pause and look at example 2. All right, let's move forward then. So we've got example 3 here, all right? And then just because we did it on the previous one, I'll highlight this. Let's remember at the end, as we get down to our solutions, we want real solutions of x, all right? But otherwise, pretty straightforward with our equation. And then on example 2, we didn't do u substitution because we already had that quadratic factored. I'm just also going to sort of skip u substitution here just so we can sort of get in the habit of not having to do that every time. But if you feel like it's useful to you and it's important, feel free to do that. You know, there's no stopping you there. But I can see that I've got 2 terms on the left and 1 term on the right. Not the biggest fan of that, so I am going to just move that sine squared x over on the left, so we're getting all of our terms on the same side. So adding sine squared x, left-hand side, and then I'll just reorder it in a nice sort of quadratic format by swapping the 2 terms commutatively, and that'll leave 0 on the right. So looking at these coefficients of 1, -2, and +1, I can see that this will factor with, and if I just did the coefficients here, that'd be 1, -1, 1, -1, right? If I was just doing that with the coefficients. So if we were doing this with x, that's how that would work out. But we're using sine of x, so I'll go ahead and swap that out. All right, so sine x minus 1 times sine x minus 1 is equal to 0. Right, you've kind of got some options here at this point. You could put that together and say sine x minus 1 squared is equal to 0, and then you would square root 0 and just get 0 and then add the 1. Or if you're going to do this with the zero product property, each of those factors individually would be equal to 0. So for example, sine x minus 1 is equal to 0. We don't really need to do that twice because we have the same factor in that factored form equation, right? So we really only need to be solving this one way. And this answer will just sort of for us. So it'll end up being the same answer. So basically we're looking at sine of x is equal to 1. Right? And that is occurring when x is equal to pi over 2. All right, so now we can hop in with our final answers here. Were there any restrictions? No, it was just sine of x, and sine is the domain of all real numbers. So there are, and in terms of solutions, we wanted all real solutions for x. So that means pi over 2 plus 2 pi k. That way we are accounting for all our coterminal angles. And we cannot forget to mention that k is indexed by all of the integers. All right, a little example 3 for you there. All right, let's push forward in this then. Here we go, on to example 4. All right, solve the equation 4 secant squared theta minus 4 secant theta minus 15 is equal to 0. All right, so off the bat, I can see that we've got a secant, which is not continuous. So I've got to investigate the restrictions here. All right, remember that secant of theta is 1 over cosine of theta. And that would mean that cosine of theta cannot equal 0. So in terms of which angle measures would give us that output of 0, that would be pi over 2. and 3 pi over 2. So both of those angles are restrictions for theta. And we don't have to be messing around with any additional whatever because we are just working in the interval from 0 to 2 pi. All right, but now let's go ahead and factor that equation. Again, like I said, if you are feeling like you want to do some new substitution, you are absolutely welcome to. I'm actually not going to at this step because I'll still factor without needing that, and then the factors sort of work out by themselves. All right, so in order to do this, I'm going to set up a box for this. And again, as I say whenever I have this factor box, if you can do it without the box method, like you can just sort of see the numbers and they speak to you, perfectly fine, right? But if you need the box, there's no harm in doing that. So take my first and third coefficients, the 4 and the negative 15. I'll put those in the appropriate spots in the diagonals. Looking at my factor boxes in my equation, I know that these two numbers, those two need to sum to negative 4, which we're getting from our middle coefficient. And then I know that they need to multiply to negative 60. Right, getting that from the 4 times the negative 15, right? Remember that numbers in the opposite diagonals multiply to the same number, right? So 4 negative 15 giving us a negative 60. So I'm thinking, what numbers add to negative 4 and multiply to negative 60? 6 and 10, that's very nice, I like that, 6 and 10. And then to make it a negative 4, we would need a negative 10 and a positive. Right, and so now at this juncture, I'm just pulling out greatest common factors from rows and columns, and just making sure that the signs work out. I can see that I've got my negatives here, so that'll be a negative 5. And if I've got a negative 15 here and a negative 5 there, I need a 3 over here. And looking at my 6 and my 3, I'll need a 2. And if I put a 2 here, then I need a 2 there. All right, well, quick maths, shablam, shablam. And now we've got our factors. All right, so let's go ahead and just write those up. So in factored form, 2 secant of theta minus 5, right? So that's coming from these coefficients here, and remembering that we are using secant of theta in place of x, because it's not a normal quadratic equation. And then 2 secant of theta plus, and all of that is equal to 0. All right, now we can use some zero product property. So 2 secant of theta minus 5 is equal to 0. And our other factor is also equal to 0. So 2 secant of theta plus 3 is equal to 0. And now I can solve each of those individually. So adding 5 and dividing by 2, quick maths. Secant of theta is equal to 5 halves. Then subtracting and dividing by 2, quick maths. Negative 3 halves. Right, we don't have an inverse secant that we use in our calculator, so we're going to use our reciprocals. Knowing that secant of theta is a reciprocal function of cosine, we know that cosine must be equal to the reciprocal of the secant ratio. So if secant of theta is 5 halves, cosine of theta is 2/5. And likewise, in our other equation, cosine of theta is equal to negative 2/3. All right. And if we were just going to be solving for some more, like ratios, we had to evaluate the tangent of arc cosine of yada yada. We could just do that with our, triangles and Pythagorean theorem and all that, but we actually want the angle measures here. So just because you see a nice fraction, a nice rational number, doesn't mean that you're breaking out triangles and solving with Pythagorean theorem. Right? We're actually trying to get exact values for theta, which we weren't doing in those types of problems before. So now we need to be using our calculator. So theta is equal to inverse cosine of 2/5. And over here, theta is equal to inverse cosine of negative 2/3. All right, now we can sort of go about each of these individually. So in my calculator, I will do inverse cosine of 2/5, and that is telling me that theta is approximately equal to 1.159. All right, if I'm to draw those axes, I know that inverse cosine is only working in quadrants 1 and 2, but I have a positive cosine ratio, so that means I'm quadrant 1. So 1.159. All right, and if we have a positive cosine, that means our other angle will be in quadrant 4. So this quadrant 4 angle can be found by using 2 pi minus the reference angle. So 2 pi minus 1.159, and that is approximately equal to 5.124. Right, doing that in the calculator. And if we pop on over here, inverse cosine of negative 2/3, approximately equal to 2.301. I'll go ahead and draw my axes. Right, again, remembering that we operate in quadrants 1 and 2 for inverse cosine, but our cosine of theta is equal to a negative ratio. So negative cosine means that we will have an angle in quadrant 2. Oh boy, not an ellipse, just an angle, just a segment. There we go. All right, so remember that as you're ascribing the 2.301 somewhere on these axes, that is not the reference angle here, right? That's much greater than pi over 2. That's the actual angle measure, right? So if we are to find the other angle in quadrant 3, because again, we have a negative cosine value, so we're in quadrants 2 and 3 where cosine is negative, right? If you are to find the measure of this angle down here, you'll find the reference angle and then do some arithmetic around pi with that. Or you could recognize that this angle also measures 2.301. So we could take 2 pi and subtract 2.301. Right? And if we do so, that is approximately equal to 3.982. All right, so now it's time to write up our options at the end. Luckily, we didn't encounter any pi's over 2 or 3 pi's over 2. So we don't have to worry about our restrictions there, even though we've stated them. So now I can just write up those decimal answers. All right, and then one last look more if you wanted to pause the video and soak it up. All right, this kind of hits the end of the notes. There is one more go further problem down here. All right, I'll tell you the reason why this one is more difficult. You can see that it's going to use some quadratic factoring. You can see that it's going to use multiple angles. And in addition, it is also a calculator problem. So this is the perfect type of problem for mastery, right? Because factoring, multiple angles, calculator business, all that stuff is stuff that we are expecting at the end of this unit, right? And it really, like, you are going to have to know those well. So if you can do all of them layered up together in a nice, hearty, layered math lasagna type of problem, that's really going to check whether you've got this stuff down. All right, so I will sort of leave this problem to you for you to try out on your own, but I will give you the answers so you're able to check your work. All right, so give me a moment, I'll come back with the answers. All right, and we are back here with some answers. All right, so if you wanted to do that go further problem, this is what you will do to check your work against. All right, other than that, that kind of wraps up today. So we've done greatest common factoring, we've done quadratic factoring, and that's going to kind of put to bed the types of factoring that we will be doing. All right, so tomorrow is going to be a practice day, but it will mostly cover these types of problems, layering in things with restrictions and the calculator and multiple angles and all that jazz. All right, but otherwise, thank you for watching this video and doing some math with me, and I will see you next time.